Hello, everyone. In the previous video, we introduced infinite series. These are sums of infinitely many numbers. And we saw that in some cases, these things actually converge to give us a finite number. We focused on geometric series, and then we also gave ourselves a criterion that tells us how to rule out series that don't converge. In particular, if your elements that you're adding up, which we've denoted a sub n, if that as a sequence doesn't converge to zero, then your series cannot converge. Now, we talked about geometric series that converge, and we talked about how to rule out when series converge. But what we're going to spend the next few lectures discussing is how to tell if a series actually converges or not. Now, today we're going to introduce what's called the integral test for convergence, and we'll see that, as the name implies, we are going to use integrals to determine whether or not an infinite summation will converge. The issue with some of these convergence methods is that they don't tell you what you converge to, right? This is as opposed to, say, the geometric series, where we found an explicit formula for the sum of those series. But what we can do with these tests for convergence is we can use them to show with pencil and paper when we converge or if we converge. And then from there, we can let a computer do the work, because we can just add up finitely many terms, a lot of them, maybe the first 1,000 or 100,000 or whatever it is. And from the fact that if it's going to converge, your elements are converging to zero, eventually that tail, what you're leaving off, you say beyond 1,000 or beyond 100,000, it's small because it's all the little tiny pieces that are left off. So that's what I would like to focus on as we move forward here, talking about these series. And as I said, we're going to start today by talking about infinite series and the convergence test. Now, where I'd like to begin is not directly jumping into the integral tests, but first talking about non-decreasing partial sums. So let's imagine that we are given a summation or a series of infinitely many terms. And let's suppose that we have all positive entries here, or at least non-negative. And this is for all n. Well, this means that the partial sums are going to form an increasing sequence. So this implies that Sn plus 1, the next partial sum, if you remember the notation from the previous video, is the current partial sum plus the next element, which is greater than or equal to Sn. And that comes from the fact that An plus 1 is greater than or equal to 0. So this tells me that my partial sums form an increasing sequence of real numbers. And you remember from the previous video that the only way you can have this infinite series converge is if the partial sums converge. But what this says right here, this is a monotone sequence. Remember, we defined this a few videos ago. A monotone sequence is either increasing or decreasing. In this case, it's increasing. And we had the bounded convergence result that says that monotone sequences, if they are bounded, then they're going to converge. Now, we can actually write this as a simple result. Actually, it comes as a direct consequence, or just sort of summing up what I just said here. But it says a series. So let me write this, An, of non-negative terms. So that's An is greater than or equal to 0. This converges if and only if its partial sums are bounded above. Are bounded from above. Okay, so this is exactly the monotone convergence theorem that we talked about a few videos ago in terms of sequences. But the question is, how do we use this in practice? Well, let's show that the so-called harmonic series, so adding up 1 over every single natural number, diverges. So what we're going to do is we're going to show that the partial sums are not bounded above. Okay, so there's a clever trick to doing this, and let me show you how this goes. So the first thing that you're going to do is you're going to look at S1, which is just 1 over 1, which is equal to 1. Then you're going to look at S2, and this is 1 plus 1/2. And then I'm not going to look at S3, I'm going to look at S4. So let me show you what happens here. Sorry, S4. And in this case, you get 1 plus 1/2 plus 1/3 plus 1/4. And of course, all I'm doing is just sort of writing down what we know here. But here's where the little trick comes in. What you're going to do is you're going to look at those back two terms. And 1/3 is larger than 1/4. So this is bigger than 1/4 plus 1/4, which is equal to 1/2. So what I can say here is that, without doing any math, without actually getting out my calculator or doing some annoying adding of fractions, this is bigger than 1 plus 1/2 plus 1/2. Okay? Now, let's go up another power of 2 here. Let's look at S8. And this is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. And in this case, I again do the same thing with 1/3 and 1/4. This is bigger than 1/2. And then what I do is I look at the next 4 terms in this, and every single one of those terms is bigger than 1/8, the last term. So it's so you get 1/5, that's bigger than 1/8. 1/6, that's bigger than 1/8. 1/7, that's bigger than 1/8. And 1/8 is equal to 1/8. But now I have 4 terms. 4 times 1 over 8, that's 1/2 again. So now you might be able to see what I'm doing. This 8th partial sum is 1 plus 1/2 plus 1/2 plus 1/2. Now, similarly, if I continue this process, I can do the same thing for S16. I can say S16 is bigger than 1 plus 1/2 plus 1/2 plus 1/2. That's S sub 8. And then I'm going to get 1 more half doing the same trick again. And in general, if I take S to the power of 2k, this is going to be bigger than, in this case, 1 plus k over 2. Okay? Now, that means that if you add up a power of 2 in these partial sums, you're getting some number that is bigger than 1 plus k over 2. But this thing goes to infinity as k goes to infinity. So if you take more and more larger and larger partial sums, this s sub 2 to the k is going to be big. And this tells us that s sub 2 to the k is not bounded above, which implies that none of the partial sums are not bounded above. So partial sums not bounded above. And so what that means from our little result here, since the partial sums are not bounded above, this therefore tells us that this harmonic series, 1 over n, the sum of 1 over n, diverges as well. Okay, so that's a nice another negation result, right? We're being very, very negative right now. We're talking about ways that we can rule out convergence. But now let's talk about the integral test. And the way that I want to do this is I want to start with an example to illustrate what I mean, okay? So the integral test is going to tell us when we converge. So let's ask ourselves the following question. Does this sum, so 1 over n squared, converge? So we just saw 1 over n. So let's ask ourselves, does 1 over n squared converge here? Now, here's what I want to do. I want to offer a little sketch before I do anything. So this is my x, this is my y. And we've seen, let's use the graph of 1 over x squared. Okay, so this is y is equal to 1 over x squared here. And here's what I'll do. First of all, I'm going to say that my partial sum, this is equal to, say, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, all the way up to 1 over n squared. And in this case, if this is my function, so if let's put this maybe in green, if f of x is equal to 1 over x squared, I can equivalently write that partial sum as f of 1 plus f of 2 plus f of 3 all the way up to f of n, right? So it's kind of starting to look like a Riemann integral or a Riemann sum. And in fact, that's exactly what's going to happen here. So let's say along the axis here, if this is 1, 2, 3, 4, 5, 6. Well, what we can do is we can put integrals directly underneath, or sorry, put rectangles directly underneath this curve. So let's look at this. Here is f of 2. And here's a rectangle that lies directly underneath this curve. And so you can see that the area from 1 to 2 is smaller, or the area underneath the curve from 1 to 2 is larger than the area in my rectangle. But that means that my area in my rectangle is just the base, length 1, and then times f of 2. So maybe let's put this in a different color so we can see it nicely. Red will be okay. So area equals f of 2, 1 times f of 2. Similarly, if I do the same thing for 3, I go up to f of 3 here, and now I have another rectangle, and the area of this rectangle, sorry, is equal to f of 3. And I can continue to do this, right? I can go up to f of 4, and then I can go up to f of 5, and so on and so forth. And the point is, if I sum up all the areas of these rectangles, it's smaller than the area under the curve from 1 up to the number I sum to. Alternatively, this is f of 1 plus, and this is smaller than f of 1 plus the integral from 1 to capital N of 1 over x squared dx. Why? Because if you discretize that integral with delta x equal to 1, you get my rectangles that I have drawn on the picture. The f of 1 is in there because I never went up to f of 1. But that's fine. That's just the first number. That doesn't bother us. And this thing tells us you can let n go to infinity here because this thing is positive. So this is just smaller than the total area underneath the curve because you're continually adding things that are positive, these rectangles. And so I get f of 1, and this is a fairly easy integral for us to do. We can actually see that this is equal to 1 itself. F of 1 is equal to 1. And boom, I've got 2 here. And so what this tells me, so therefore, all partial sums are bounded above by 2, right? That's what this is telling me here. The jump from each partial sum in terms of n to all partial sums for every n comes from right here, from letting the upper integration bound go from n to going all the way up to infinity. And so from our result, this implies that the sum of n equal 1 to infinity of 1 over n squared, this thing converges by that result that I just had on the previous board here. So if we go back and look at this, it says that a series of non-negative terms, 1 over n squared, those are non-negative, they converge if and only if the partial sums are bounded from above. Well, I just showed that my partial sums are bounded from above, so therefore my series converges. And this is basically the principle that the integral test actually relies on. So let me give you a theorem, and this is the actual integral test. And so let's write it down, and then we'll play with some applications of this. So let's say let an be a sequence of positive terms. Okay, and then suppose that we can actually write the sequence as f, as some function f evaluated at the integers, where f is continuous, and it's positive, and it's a decreasing function of x of x for all x beyond some integer. And so n is a positive integer. We'll talk about where this comes in a moment, but let's keep writing this down. So then the series, the sum n equal 1 to infinity of an, and the integral of capital N to infinity of f of x dx, they either both converge or both diverge. Okay, so what the integral test really does is it says if you can find a function that describes, jumping from point to point in this sequence, then you can translate the question of asking whether or not the series converges to whether or not the integral converges. And this should come as good news because we've been doing a lot with integrals, especially we've recently talked about integrals with an infinite limit of integration. So we can handle this. We can translate the problem of something that was originally relatively hard, finding if a series converges, to finding something that we could probably do now, because that is, in terms of an integral, something we've been working on for a very long time in this class. The other piece here is that we look beyond some positive integer. The reason for this is because if you add up finitely many numbers, that is still going to give you a finite number, right? The sum of all the numbers from 1 to 100, it's big, but it's still a number, doesn't matter. So what this is saying is that you really only care about what's called the tail. the piece that's on the end. And that's why you're talking about n to infinity. Now, in the case of our integral example that we did right here, capital N was equal to 1, so it didn't matter, right? Essentially, we saw that it came down to the fact that our function f of x, the integral converges, and we use that to bound these partial sums. Now, this is exactly how you would prove this theorem. I'm not going to do it, but the proof looks a lot like how we went through this example. What I would like to do is I would like to present some examples here and you see how we can use this in practice. So in particular, let's generalize our first two examples. Let's consider the series n equal 1 to infinity of 1 to the power of p. P here stands for power, where p is greater than 0. So we want to have positive powers. We would like to ask ourselves, when does this thing converge? Right? When do we have a convergence sequence? So first, we already saw the series diverges when p is equal to 1. That's the harmonic series, 1 over n. And it converges when p is equal to 2. We don't know what it converged to when p is equal to 2. In fact, I can tell you, I believe it's about pi squared over 6, but it takes a lot more work. That's much heavier machinery, much heavier mathematics that needs to show you that. All this can do is tell you if you converge or not. If you do converge, then a lot of the time you can just use a computer to approximate what the summation is going to be. Okay, so let's let f of x equal to 1 over x to the power of p for x greater than or equal to 1 and any p greater than 0. Well, we did this previously. So from our previous work, we saw that the integral of 1 to infinity of 1 over x to the p dx is, or this thing is finite if p is greater than 1, and it is infinite if p is less than or equal to 1. So you might have to go back in the videos or in your notes to find this. We did this with improper integrals part 1, but we proved this, right? We went through all of the possible cases, and we saw that this series, or that this integral, it converges, it gives a finite number as long as p is larger than 1. But if p is less than or equal to 1, this integral is infinite. So therefore, the series 1 over n to the p converges when p is greater than 1 and diverges when p is less than or equal to 1. And so what you can see here is that p equal to 1 is the borderline case, right? This is the harmonic series that we talked about. That thing takes a very, very long time to diverge. And what's super weird, for example, what if I use this? That number is bigger than 1, which implies that the sum actually converges for that value of p. Now, if you'd like to, you can program a computer to sum up the first, 1,000 or 10,000 terms, and you'll see that it takes a very, very, very long time for this to converge. Whereas for large values of p, say p equal to 100 or something like that, then this series is going to converge very, very quickly, because 1 over an integer to a very large power is extremely small. That thing is shrinking super, super fast. Again, just think in terms of what these graphs look like and who is under who. Okay, let's take a look at another example. So this is, again, very related to what we saw in with these improper integrals. So we're going to use the sort of same examples that we did there. Let's look at 1 over n squared plus 1. Okay, does this thing converge? Okay, so first of all, this is not in the form of the previous examples, right? It is 1 over n squared plus 1, not just 1 over n squared. But we can set f of x equal to 1 over x squared plus 1, right? Because this tells me that my sum of n equal 1 to infinity of 1 over n squared plus 1 is just equal to the sum from 1 to infinity of f of n. So it's my function evaluated at each integer. And then we can take this integral from 1 to infinity of f of x dx. So we're using capital N is equal to 1. And this is going to give me the integral from 1 to infinity of 1 over x squared plus 1 dx. Now, you've probably been doing a lot of integrals. This is probably one that you've gotten good at, especially if you spent some time doing partial fractions. You remember that this is the arctangent. If we want to do this properly in terms of limits, this is the limit as b goes to infinity of arctan of x running from 1 to b, which is the limit as b goes to infinity of arctan of b minus arctan of 1 is pi over 4. And you might have to dig out some sort of resources here to remind yourself what the arctangent function looks like. But arctan as b goes to infinity becomes pi over 2. So we get pi over 2 minus pi over 4, which is equal to pi over 4. So the integral is finite, and therefore the integral test gives that the sum, sorry about that one, that's a little ugly, I'm trying to squeeze it in at the bottom, 1 over n squared plus 1 converges. Again, I want to emphasize it does not tell you what it converges to. It just tells you that it converges. This is something you have to be very, very, very careful with, right? There is actually there is a relation between the values of the integral and the values of the series, but it is not that they are equal, right? It's just in terms of error bounds that we're not going to speak about in this lecture. So this is just answering yes or no. Okay, let's keep going. Let's look at another example. Again, same problem. Does this series converge? N e to the minus n squared converge? Again, we can use the integral test. Let's set f of x equal to x e to the minus x squared. And then we're left with the integral from 1 to infinity of x e to the minus x squared dx. We would like to know if this thing is finite or not. If you want to solve this properly, you're going to let u equal to x squared. And this gives you du is 2x dx. So it's a substitution problem. If you do the substitution here, you get 1/2. That's coming from the dx substitution. The integral from 1 to infinity, the bounds don't change, of e to the minus u du, which if we translate that upper bound back into a limit, so if we just want to do the notation properly here, the antiderivative is fairly easy to find. So we got e to the minus u, and this is running from 1 to b. We don't need to do any back substitution now that we've translated the bounds in terms of u as well. So we don't need to put it back into x, right? It's a definite integral. And so this leaves me with the limit as b goes to infinity of minus 1/2 e to the minus b. plus 1/2, and then e to the minus 1. Letting b go to infinity causes the first term to go to 0. So I'll just make a little notation of that like this. And this leaves me with 1/2 e to the minus 1. I don't know what that number is, but I do know it's a number. I know it's finite. So therefore, by the integral test, my series converges. N equal 1 to infinity, n minus n squared converges. Okay, let me do one more example here. And if you're wise, you could probably anticipate that this one will diverge, since I've done a lot of converging problems. But nonetheless, let's work through the math. The nice thing about this integral test is it translates a question that is relatively new and hard potentially, if series converges, into one that is old and potentially easier for us. And that is, does the integral converge? Can you compute the integral? Which again is probably something we've gotten pretty good at. So 1/2 to the power of the natural logarithm of n. Does this thing converge? Okay, so let's set f of x equal to 1/2 to the log of x, or the natural logarithm of x. And so in this case, we're going to do the same thing. So then we have an integral from 1 to infinity of f of x dx. That's 1/2 to the ln of x dx. In this case, we're going to have to do some substitution again. This one might take you a little bit longer to come up with, but we're going to let u equal to ln of x. And so this is going to give me du is equal to 1/x dx. And also, what I can do is I can rearrange. So this also tells me that x is equal to e to the u, and that's using the fact that u is equal to the logarithm of x. So I raise both sides to the e, and this tells me that I get, say, e to the minus u dx here. And putting this all together gives me e to the u du is equal to dx. So let's see what comes out of this, right? This is a complicated substitution. By no means should anyone consider this one an easy one. My lower bound becomes 0. That's plugging 1 into ln of x. The upper bound remains at infinity, since ln of x goes to infinity as x goes to infinity. Now the substitution for dx leaves me with e to the u and then du. And here I have 2 to the power of u. And these are two numbers to the power of u. I can group them together. E/2 to the power of u. Now, remember, e is about 2.718 or something. So this is a number that's larger than 1 in here. 2.718 divided by 2. That's bigger than 1. And I can find the antiderivative of this. You can think of that as a to the power of u, right? The antiderivative is the function divided by the logarithm of the base. So 1/ln of e/2. And then, well, let me put the limit out front first, just so that things look proper. The limit as b goes to infinity. 1/ln of e/2. That's the natural logarithm of the base. And then times e/2 to the power of u from 0 to b, which is equal to the limit as b goes to infinity of 1/ln of e/2. So I'm just going to expand this out. E/2 to the b minus, now plugging in the lower bound at 0 leaves me with 1 over ln of e over 2. But as I mentioned, e over 2, that is larger than 1. So maybe we can put a little note. E over 2 is larger than 1. And so what that means is that taking successive powers of it goes to infinity. So this limit is infinity. And therefore, the integral of 1 over 2 ln x dx diverges, which tells us that the series must also diverge by the integral test. 2. Okay, so a lot of what you can see we've done is just transferred things into an integral problem. And again, I just want to close by emphasizing something that I've said a few times, but this by no means tells us what we converge to, right? Just because we can figure out what the integral is equal to, that does not necessarily tell us much or anything at all about what the series converges to. For example, maybe if I share my screen just to close this off, if we look back at where we started with this 1 over n squared term, we saw that the integral, if you use the integral test here, you get 1. Whereas I mentioned that the sum of this thing is pi squared over 6. So if you think of pi being close to 3, pi squared is close to 9. It's a little more than 9. And then divided by 6, we're looking at something about 3/2, so 1.5. So it's quite a distance off from the value of 1 that you would get from the comparison test, or this comparison with the integral. But nonetheless, what we've done today is we've seen how we can translate a relatively hard problem, finding if a series is convergent or not, into one that should be a little bit more accessible, at least, that is using integrals. So we'll continue our exploration of these convergence tests in the following lectures.